In this clip, I wanted to tell you briefly about how things at the nanoscale are impacted by fluid forces, and they behave differently than things at the macro scale that we're used to. But before we get started, I want to recommend an article that's at the end of your chapter called Life at Low Reynolds Number. This is a great article written by a physicist where it talks at a very high level about what your life would be like if you shrank down to the size of a bacteria and tried to swim. And it would be very different than how you have learned to swim in a swimming pool. And the reason is because the Reynolds number and the way it changes the fluid forces that are present when you're very, very small. So I highly recommend this. Take a look. It's a great article. It is not heavy on the math, but it does a great job of explaining things. But I wanted to give you a quick example of what things are like in nanoscale dimensions. So at the nanoscale, typically you're talking about Reynolds numbers that are much less than 1, or even much less than 1. And so very small Reynolds numbers, which means that the viscous forces dominate. It's a very viscous environment. It would be very much like jumping into a swimming pool full of honey or molasses and trying to swim in that. And so I want to tell you how things actually change given that environment. So what I want you to do is imagine a scallop that lives in the ocean. And the scallop's very interesting. The scallop swims basically by closing its shell, slamming its shell shut, and squirting water out, ejecting water. And so when it slams shut and ejects the water, that generates a forward motion. It propels the scallop some distance. It shoots it forward. So basically it squirts out the water. So it squirts out water and then it coasts. So after it squirts, it then moves a little bit. So in the tea and milk example from the last video, when you stopped stirring and the water still moved around, this is sort of a similar phenomenon. There's still inertia. The scallop has inertia. So if you were to do a Reynolds number calculation on the scallop, it's an external flow, you would find that the Reynolds number is pretty low. It's definitely laminar, but it's not nearly as low as what you would see in a nanochannel. So the scallop slams shut, squirts out some water, and as a result it moves. It moves some distance. And it does this over and over. It opens up again and squirts out and moves and moves and moves. And this is how it moves through the water. So now what I want you to do is imagine that you have an attack of evil and you find a scallop living happily in the ocean and you take it out of the ocean. And you take it from its saltwater environment and instead you put it in a tub full of molasses. And you want to see what happens to see if it can swim. Well, the poor scallop's going to try and swim, of course, because that's what scallops do. So it's going to open up in the molasses, and then it's going to try and slam shut. But what's going to happen is the molasses has a much lower Reynolds number than water, because the viscosity is much higher. So water has relatively low viscosity. Molasses, on the other hand, has a relatively high viscosity. And as a result, this is going to be a small Reynolds number, but this system's going to be much smaller. Okay? So the molasses, so the scallop's going to open and then try and squeeze shut to move. Well, when it opens and then goes shut, it's going to move forward a little bit. It's going to try and squirt the molasses out. I'll use a different color for molasses. Right? So it opens and then closes, and it goes a little distance. Now, there's something interesting to note here. This distance is less than this distance. And the reason is there is no inertia. there's no coasting once it closes. So it squirts molasses out, but there's no inertia, so it doesn't go as far. And then an interesting thing happens. When the scallop opens back up, right, it actually will travel backwards to the exact same starting location because it's essentially stuck in molasses. So the scallop will essentially go forward and backward, forward and backward. It'll stay in the exact same place. And the reason it stays in the exact same place is because there's no inertia to help propel it forward. This is a direct consequence of a very low Reynolds number. And the technical term for this is you cannot use reciprocal motion. You cannot use a reciprocal propulsion method to move something back forwards in a nanofluidic system. So this is why, in fact, bacteria don't look like scallops, right? Bacteria typically have flagella that move in a corkscrew-like motion, and this gives the bacteria a non-reciprocal propulsion method, and as a result they can move forward. So if you could genetically engineer a bacteria to have essentially bacterial oars, a bacteria that had oars and tried to move these backwards and forwards would not live very long because it would just go back and forth just like the scallop. So if you genetically engineered a bacteria like this, it would very quickly go extinct because it couldn't go anywhere to get any food. And so this method of propulsion is ineffective at the nanoscale. So reciprocal motion, anything that uses reciprocal motion at the nanoscale can never move. And so that leads to all sorts of interesting questions, which is how do we move things at the nanoscale? And nature has solved this problem by evolving all sorts of different designs on bacteria that use flagella to get them to move forward. And this is also why when we think about how to move nanoparticles, for instance, you're going to have to use different methods to move them rather than methods that work at the macro scale. And this, of course, also leads to the question of what forces become dominant. So at the nanoscale, at these very short distances, one thing that becomes very effective is diffusion. And I'll tell you about diffusion a little bit in another video.